People, welcome to a new unit. We'll talk about two main concepts that center around a big one: momentum. Okay, momentum is something that we've heard most of us in some figurative sort of references, but it's something that in physics you really won't be asked to define. The definition is a mathematical one. So we'll just start with that. All right. First of all, the variable we use for momentum is that. It's like a lowercase p, but a little slicker. It's a Greek lowercase rho, but we'll still call it p. By definition, momentum is the product of an object's mass and its velocity. That's it. That's the definition of momentum. So there's a good place to start. All right. We've talked about that as a property of objects. Objects have properties like mass and inertia, but here we talk about the product of mass and velocity. The big deal is that since velocity is a vector, so is momentum. And whatever direction velocity, an object's velocity is in, its momentum is in that same direction. That'll be really important when we get to some later situations. All right, and the units for momentum are the units of, well, mass times the units of velocity. So that means, well, units of mass, kilograms, units of velocity, meters per second. There are the units for momentum. It looks a little bit like a Newton, right? Except the Newton is a kilogram meter per second squared. So we'll get to in the next slide how there are also other ways to express the units of momentum, but that's the most common one, the kilogram meter per second. Okay, so dump truck, right? Dump truck, tons of mass, moves at a certain velocity, has a certain momentum. Okay, a little girl on a tricycle has a much smaller mass, moves at a certain velocity, has a certain momentum in the opposite direction. What we'll eventually talk about is what happens if these two, can I do this? Oh, if these two objects interact, all right? The goal of this unit, one of the main goals is to investigate what we call two-body interactions, all right? And then some interactions we call collisions. No girls on tricycle were hurt in the making of this video, just so we're all sure. Could these two objects ever have the same momentum? Well, sure they could. Sure. You tell me there's one really easy way for them to have the same momentum. You tell me. Second, well, let's say this little girl on the tricycle has a mass of, I don't know, about like 18 kilograms, right? And let's say she's cruising along at, I don't know, 4 meters per second, right? And, well, her momentum, therefore, is m times v, and that's, well, 18 kilograms times 4 meters per second. And if my math is right, that's 72 kilogram meters per second squared. Now, kilogram meters per second, not per second squared. Notice I'm not talking about the direction here. I'm just choosing to talk about the magnitude of this momentum. So let's look at the truck and what we'd have to do with this truck to give it the same momentum as the little girl in a tricycle. Well, I'd say that this truck, I don't know, how about 10,000 kilograms, right? Each kilogram weighs 2¼ pounds, so that's 22,000-ish pounds. That's 11 tons of a pickup truck. Sure, sounds fine to me. Maybe not even big enough, but close enough. So this truck would have the same momentum as this tricycle. Well, we'd have to sort of start here, and we'd have to find out what the velocity would have to be. Well, we're saying it's still 72 kilogram meters per second. And 10,000 kilograms. Well, that looks like V would have to be 0.00072, right? 1, 2, 3, 4, 5. Oh, wait, 3, 4. 1, 2, 3, 4. Sorry, 0.072. So the truck would have to move at 7.2 millimeters per second in order to have the same momentum as that little girl. Possible? Sure. Reasonable? No. All right. But it's certainly possible for objects of different masses to have the same momentum. So this is the, well, like I said, there's an easier way. You tell me what that real straightforward, definite way to give them the same momentum is. Okay? Next, impulse. Now, impulse does have a real definition. An impulse, by definition, is a change in momentum. All right, we use the variable capital J. Why not? Why not use I? Well, I is reserved for electrical current. Well, why doesn't current use capital C? Well, it's reserved for capacitance. And we could go on and on. So yeah, J. J by definition. Simplest equation we can use for J. Well, there's what J is. J is a change in momentum. It's the definition of J. Well, here's an object. And let's say this object is moving this way. We want to change its momentum. Well, what does that mean, or how do we do it? Well, we got to change its velocity. You're not going to change an object's mass. All right, so if we change its velocity, well, we've changed its momentum, and therefore it's experienced some impulse. So we could write this like that. If we do, well, since momentum is mv, change in momentum is m delta v. Fair enough? Well, how do we do that? So this thing's moving along at a certain velocity like this. How do we change its velocity? Well, here's one way. We could push on it. Apply some net force, let's say that way. All right, so apply a net force. All right, and let's see. So actually, this mv, there's something about force and m and delta v that sort of, well, we've seen this, right? Net force equals ma, which says that net force is m. What's the definition of acceleration? It's the rate of change of velocity. Well, look, we can isolate m delta v, which we said is a way of finding impulse, by doing that. So we end up with m delta v is net f times t. So here's another way to calculate impulse. So this ends up being like one big, long equation that you'd never use all four parts of at once. You choose which two parts are the most appropriate to use based on what you're given and based on what a question asks. Okay, and what we're saying here is, you know, you can't, well, the act of applying a force by its nature takes some time, has to occur over some amount of time t. All right? And by definition, the product of that net force and the amount of time you've applied it over is going to be equal to the object's change in momentum, or the object's impulse. All right. It's nice to notice in this, whoops, not clone, delete. It's nice to notice here that there are some kind of parallels between work energy stuff and momentum stuff, right? We have this thing we call work that by definition is change in total energy. And, well, we said that's F times D, the product of force over some distance. Here we have this quantity impulse, which by definition is change in momentum, which we get at by the product of force and time. All right, so some nice parallels here, and for a lot of the for that reason and some others, these are units, energy and momentum, that are a lot of times looked at together, and that's what we'll do. Okay? So again, this, when do you use an equation with 4 different terms in it that are all equal to each other? Well, you never use all 4 of them at once. We'll see some examples of when it's appropriate to use different parts. All right? One thing definitely worth mentioning is, well, first of all, we know momentum is measured in kilogram meters per second, so that means that change in momentum is also measured in that, which means that impulse is also measured in that, right? So impulse, J, change in momentum, M delta V, those are all, yeah, sure, I get it, kilogram meters per second. Right? But this shows us also that if we look at the F delta T part, or the FT part, that means that we can express impulse in FT units, Newton seconds. Right? And sure, remember what a Newton is? It's a kilogram meter per second squared. So if you multiply both sides by seconds, yeah, a kilogram meter per second is a Newton second. Not a Newton per second. That's not what this says, right? It says Newton seconds. Kind of like work is in Newton meters, not Newtons per meter. That's K, spring constant. But a joule is a Newton per meter. Impulse measured in, did I just say Newton per meter? Newton meter. Impulse measured in Newton seconds. All right. Now, could you express impulse in kilogram meters per second? Yes. Can you express momentum in Newton seconds? Sure. They're the same thing. Most appropriately, we express momenta, that's the plural of momentums, or momentum. Momenta, typically measured or expressed in kilogram meters per second. Impulses, typically, most appropriately, maybe expressed in Newton seconds. But they're equivalent. Okay? Okay. Here's an example. There's a car, 24 meters per second. Stops. Oh, I'm going to add a little caveat. Traveling east at 24 meters per second. Stops by applying its brakes over a period of 7.5 seconds. What impulse does the car experience? Well, if you want, you can start with this whole thing. Those are all ways of expressing or calculating impulse. So what do we know? We know a mass. We know 24 meters per second. Oh, and we know stops. So that means we know a delta V. All right. If we say that east is positive, then our V naught or VI, depending on how you want to express it, is 24. Our V final is 0. So our delta V negative, right? And again, we know M, we know delta V, so I'm going to say that J, or you could write delta P, same thing, is M delta V. That gives us 36,000. What's that? Oh yeah, they're the same thing, kilogram meters per second, or Newton seconds. But it's negative. I'd say most appropriate answer is probably 36,000 Newton seconds west. Right? West. Get me? If east is positive, our answer is negative, that means west. Momentum's a vector. So is impulse. It's a vector. Because delta V is a vector. Oh yeah, so is net F. All vectors. Part B. What average force do the brakes apply? Well, the brakes apply the net force. There's nothing pushing the car forward. So now we can really say that net F times T is the same as the impulse. I'll go back to the numerical way here. Whoops, not joules. That's tricky, right? J is impulse, but the unit J means joules, not the units of energy. These have to be the units of impulse divided by our, what, 7.5 seconds. So we get most appropriate answer probably west. Right? How do you slow a car down that's driving east? You have to push west. Sure. Okay? Okay? Yeah, impulse with graphs is a very common way to look at this stuff graphically if we plot force as a function of time. All right? And if in a certain case, I don't know, a case like this, let's say there's a force F1 that's applied for some amount of time that we'll just call T. Well, we can say that for case 1 here, just multiply those two together. If we know what those numbers are, those values are, right? Let's look at a second case where it looks like this. So in case 2, we could say that in general J is Ft, and well, I guess F2 and well, notice, if you will, here that let's call this J1, call this J2. F2 is half of F1, right? But the time is the same. Right? Same thing? Well, this is J1, right? So this says, sure, if we apply half the force for the same amount of time, what we get is half the impulse. Fair enough? Let's look at a third case where we do this. Oh, I'll stop there. Really, I should stop there. We'll call this, whoops, F3. And so we could say that this is case 3. J3 is F3. Well, let's call it, I don't know, T3, right? And notice that F3 is 2F1, and T3 is, well, half of the original amount of time, T. And that gets us F1T, or that J3 equals J1. So we can get the same exact impulse, the same exact change in momentum in lots and in an infinite number of ways, an infinite number of combinations of force and time. But notice, in case 1, we apply a certain force for a certain amount of time. In case 3, we get the same impulse by applying more force, but for less time. Make sense? Now notice also that what are we actually finding when we do F times T on this graph? Let's look at the example of case 2. Well, F2 times T is just like saying base times height. So J2 is F2T, which is the same as, well, I guess, quote, height times base. So, big deal. For this kind of graph, impulse is area. Slope doesn't tell you anything because there's nothing that we do that's newtons per second. But Newton seconds, or F times t, oh yeah, that's impulse. Okay? Good to go? All right, now we'll put some numbers in. Let's say, I didn't put numbers in yet, but let's call this, what's that ratio? I don't know. Let's call this 2 and 5. That's a seconds. And let's say this is, I don't know, 30. Okay? At time t0, there's a mass. Moving to the right, there's an initial velocity. What's the total impulse? Well, two ways to do it. One way is J equals area. So find the area of each of those shapes. All right? Which is the same thing as, really, we'll call this like interval 1 and interval 2. It's the same thing as saying F1T1 plus F2T2. But here's what you have to do. Some of you have already picked this up, I bet. This one's easy, right? Nice constant force. F times T. Done. This one, we have a force that varies linearly from one value to another. One of those values happens to be 0. But what we really have to make sure we always do is that average. Okay? And whether or not you're thinking of them as areas or thinking of doing F average times T, you're doing the same physics. All right? I prefer to stick with the, let's really make sure we're thinking physics style. So I'm going to do that method. And I would say that, I don't know, the total impulse is F1 average, that's 15 newtons, T1, 2 seconds, plus F average 2, 30 newtons, T2, 3 seconds, not 5 seconds. This interval, 3 seconds, right? So 30 plus 90, that's 120 Newton seconds. Okay? The change in momentum. Oh yeah, same thing. Yeah? What's the speed at the end of this interval? Well, let's see. We want a V final. We know a V initial. We know a mass. I'm going to do this. Go. It's okay? Recap. 1. Momentum. It's a vector. It's the product of mass and velocity. It's measured in kilogram meters per second. Okay, fine. 2. Come on, stop it. Just like to have things centered, don't we? Don't we? Impulse. J equals delta P, which you can find by doing M times delta P, or you can find by doing F times T, net F times T. Also measured in kilogram meters per second, or Newton seconds. Is there anything else really to recap? I mean, sure, we could, one nice thing to recap is that you have this graph. I don't care what the graph looks like. It could look like that. We won't ever solve that problem, of course. But if you want to know net impulse, Well, it's always F average times T, and what we really have to do is let's do that area, total area. Now, the more likely scenario for us, like we said, is that we wouldn't ever do all some crazy graph like that, right? I can't ungroup. You know, come on, will you? No. Well, sorry, people. I'm not as dumb as I look. The more likely scenario, of course, is that we would do like, ooh, here's a crazy one. You could have like this, and that, right? What I would say is you can either find each one of those areas, 1, 2, 3, or like we said, we could just do that. It's the sum of all the F average T's. You get what I'm saying? Each one of those intervals has an F average and a T. Find them, add them up. Okay? Okay, folks. See you tomorrow.